Welcome to the course on principles of vibration control. We have reached the fag ends of our journey on vibration control in this course. Now, in the remaining lectures, I want to focus about the active vibration control. So, towards that direction, we are working on state space control, and for state space control, we have to first of all we have talked about that how to develop the state space model, but today we want to talk about certain canonical forms which will allow us to develop the modern control, that means full state feedback control for vibration control itself. Now, the first thing we have to keep in our mind, and I will actually prove you that after a few more slides, that state space representation is not unique in nature. Remember, I told you that depending on the choice of the states, the state space matrix will change, but that does not mean that the governing ODE equation will change or the dynamics will change. We will prove it, because one of the most important telltale criteria towards that is the eigenvalues of the system will not change. So, no matter whatever will be your choice of state vectors, we have to finally cross check that. Now, since let us first of all assume that this state space representation is not unique in nature. So, we are looking for certain forms which we are calling to be the canonical forms. Canonical in good old days has a relationship with canon itself. Anything which will be said by church with a canon sound would be considered to be the last word in that direction. But as far as our things are concerned, these are certain very uniform forms that is used all over the world, and hence this canonical form term came, and this we will learn corresponding to three cases. One is for controller, another is for observer, and the other one is called Jordan canonical form. There are a few more, but these three are generally most useful. So, we will first talk about the controller canonical form. Now, if we consider the governing equation of the system in a bit generalized manner, if you can see that this is the governing equation of the system, where it is a nth order ordinary differential equation, and this is y is the dependent variable and time is the independent variable. So, left hand side gives us that up to dn y dtn nth order, and right hand side we have this u which is the control effort. So, right hand side also I get up to mth order, or up to that kind of a, I mean you need not go up to n here, you can go up to something like n barth order or something like that, where n and n bar need not be the same. So, that is what is is our governing equation of the system, where left hand side talks about the states, right hand side talks about the control effort. Now, this since this is having an nth order, let us say governing ODE of in terms of y. So, as a function of t. So, this equation can be actually decomposed into n first order equations. N first order equation, and that n first order equation is going to give us the state space format of it. Now, in that state space format, the controller canonical form should be such that all these coefficients are only coming at the last row of the A matrix. So, in the A matrix, it will start with a representation of 0 1 0 0 0. So, if you look at it, that this is your diagonal actually, and then the super diagonal terms are all unity. So, you can see that these are the super diagonal terms which are all unity. That is the way it is arranged, and all other terms are 0 here, and below also all other terms are 0 except the last row. So, this block is 0 and this block is 0, and in the last row we are getting these coefficients back from the characteristic equation, which is minus alpha n, then minus alpha n minus 1, like that it will go up to minus alpha 1 coming as the last term of this. That is the way if we can represent the A matrix, and then the B matrix, that is the actuator influence part. Remember again that we are talking about the form x dot equals to A x plus B u. So, this B matrix, all the entries will remain 0 except the last, which will be unity. That is what will be our B matrix, and I earlier told you that we can develop an output matrix, which is y equals to C x. Sometimes it is extended up to y equals to C x plus d u if the control effort directly affects some of the outputs. So, in this case for control canonical form, the C matrix will have this following form, okay, taking coefficients from the two sides, and D matrix is simply beta 0. So, this is what if we develop these nth order ODE by decomposing it first into nth first order, n first order equation, and then writing it in this ABCD form, then we are going to get the controller canonical form of the system. So, this form will be useful for us, that is why we have to always keep this form in our mind. There is another one which is known as the observer canonical form. So, this is just the dual of the controller canonical form, and that you can see that why this is the dual part of it. You can easily see it if you look at the structure of the A matrix here. Instead of the last row, now it is the first column where all these coefficients are appearing starting from minus alpha 1 to minus alpha n. And then if you can see that once again the super diagonal terms are unity here and no other terms are coming into picture. B matrix is not 0 0 1 now. B matrix has all these based on the coefficients drawn from this governing equation. C matrix is 1 0 0 0, that is why that C matrix is supposed to be corresponding to the output equation y equals to C x plus d u, where y is the output, and that is why this is, we put more focus on this, that this is related to what you call the the sensing. Okay. So, this is the sensing, like B is the actuation, this is the sensing okay, influence matrix, and of course, D is the disturbance. D is the disturbance. So, here that sensing part, because observers are related to sensor, wherever we cannot actually have sensors to sense a particular state, we try to estimate that state, and then this observer canonical form becomes useful, because we have to design, we can design an observer for this estimated state. So, that is why this part is simplified here as C is 1 and rest is 0 and D equals to beta 0. So, this is known as the observer canonical form. There is one more form that comes out, this is known as Jordan canonical form, and this is the form which is for non-repeated eigenvalues. So, once again we have the same equation in front of us, and you can actually carry out this time Laplace transformation of the entire equation. So, y will be y s, u will be u s, and you can write each one of them through a partial fraction. So, these are the partial fractions, so that you actually separate it out in terms of lambda n distinct roots. Okay. So, that is what then becomes our characteristic equation. So, now if I line up all these eigenvalues which are the distinct roots along the diagonal, rest is all 0, then that is what is my A matrix in the Jordan canonical form. B matrix is all unity, and C matrix has all the residuals corresponding to each one of these roots, all the residuals, and D is beta 0. So, this is the Jordan canonical form. So, these 3 canonical forms are important for controller design, that is why we have first introduced these 3 forms to you. Now, from this form to form, this is only about, it is like the same person whom you are putting into different dresses, dresses corresponding to your convenience, but the person remains the same. How do I prove that? That you can prove from the proof of invariance of the eigenvalues. So, if you look at it, that our initial equation is the governing equation was x dot equals to a x plus b u. Now, let us say that I do not want it in this form, I want it in control canonical form or observer canonical, some or the other form. So, let us say corresponding to that form, the state vectors are not x but z. Now, first of all we are working in the linear domain. So, let us assume that this x to z, a mapping is possible through this transformation matrix T. So, T is our transformation matrix. So, then this entire form will look like T. So, I am now writing x equals to T z. So, this will become T z dot, that is this term, then A x will become A T z and B u will remain as it is. That is what is my second stage. In the third stage, what I will do is that I will take these T out here by pre-multiplying everything both the sides by T inverse. So, if I do that, then T inverse T will be identity. So, Z dot will be T inverse A T z plus T inverse B u. Here I have made an implicit assumption. What is that implicit assumption? That is T inverse exists. Only then actually this transformation would make sense. So, and later on we will see that this is actually related to the controllability or observability of a system. So, now our new equation is a new state space equation we have obtained, that is not in the form of x dot equals to A x plus b u, but z dot equals to T inverse A T z plus T inverse b u. You may write that z dot equals to something like A tilde z, where A tilde is T inverse A T plus B tilde u, where A tilde is actually our T inverse A T. This is our new state matrix, and B tilde is actually T inverse B. Now, if this be the case, then what is the eigenvalue of these A tilde? Well, that I can always find out if I can find out lambda I minus A tilde. So, what is the determinant lambda I minus A tilde? A tilde is nothing but T inverse A T. So, lambda I minus T inverse A T, that is what we get. Now, let us say this I is the identity matrix and I write it as T inverse T, because T inverse T and the inverse of T if it exists. So, T inverse T will be identity, because T inverse T will be identity. So, identity I can replace by this minus T inverse A T, and then I can take this T inverse common from both the sides. So, T inverse it will become then lambda I minus A times T. So, this identity matrix we are keeping here just because this T I am taking to the right hand side. So, now there are 3 matrices for us, T inverse, lambda I minus A and T. So, the determinant is the product of these 3 matrices. Now, there is a rule of determinant which says that if you have a determinant of 3 matrices, product of 3 matrices A, B, C, then this will be equivalent to the determinant of A times determinant of B times determinant of C. This is what we have used here, that this will be then determinant of T inverse, determinant of lambda I minus A and determinant of T. So, if I do that, then of course, the determinants can be actually taken anywhere, matrix cannot be. So, I can take the determinant of T here and then this T inverse T would become identity. So, all that will be left is determinant of lambda I minus A. Now, you can see that I started with lambda I minus a tilde, that was giving me the characteristic equation, and I got lambda I minus a determinant. This is giving me the same characteristic equation. So, what it means is that the transformation matrix has only changed the form, it has not changed the eigen values of the system. So, the eigen values are actually invariant in this case. That is a very important conclusion that helps us that from form to form very smoothly we can jump, provided this transformation matrix exists. That is the only precondition that we have to keep with us. Now, with that we need to see a few things. For example, how do we check the stability of a system? Well, in state space form, the stability of a system will always depend on the eigen values of A, which may be obtained from the characteristic equation. If you remember that when we are talking about this transfer function based approach, then the roots, I was always telling that the real parts of the roots should not become positive, it should not go to the right hand side. That means, if I plot the S plane, if you remember the real part of S versus the imaginary part of S, I said that no poles can be placed in the right hand side, no poles, because then it will be unstable. Now, in this state space form, this pole is to be replaced by the eigen values, otherwise it remains the same. That means, the real parts of the roots or the eigen values are strictly negative, then the system will be considered to be asymptotically stable. Let us consider a kind of a system, like say this is a system. If you look at it, that this system looks like as if in a control canonical form, but we cannot guarantee because we have not seen the B yet. Only when we see the B also, then only we can say yes, it is in control canonical form. Now, anyway, our job here is to find out what are the roots, what are the eigen values of this system. Well, we can find out what is the determinant of this system, that is lambda I minus a. Keep in mind that lambda I actually means I is a identity matrix. So, it is lambda 0 0 0 lambda 0 0 0 lambda. So, I can put that and as lambda I minus whatever is my A matrix. If I do that thing, I am getting this lambda I minus a, and if I do the find out the determinant, I am going to get this polynomial, which is a cubic polynomial of lambda. Now, by using MATLAB or by using other formulations, you can actually, or Newton Raphson's, you can find out what is lambda, and you will see that these are the three roots of lambda, and then that means that this is a stable system, because the lambdas are all in the left half plane. So, minus 1, minus 2 and minus 3. So, that means this is going to be a stable system. So, that is the way we can first of all check the stability of a system. Next, what we can check is actually what is the so called the control canonical form of the system. Next, we want to talk about the controllability and the observability of the system, because particularly we will talk about the controllability, and also observability will check as a side by side with respect to the observer canonical form. Now, let us look into these forms. So, how do we define the controllability of a system? The controllability, the term itself is telling us that if we have a system where I have some actuators through which I am trying to control the vibration should be, this actuator should be placed in such a manner that it can control the vibration. For example, let me just give you something like a physical significance of what we are talking about. Suppose this is a cantilever beam and this beam is vibrating. Now, if you want to control this vibration of the cantilever beam, you have to place actuators. So, if you place an actuator here, you will be able to control. If you place it somewhere here, the effort will be increasing, but still you will be able to control. If you place it very close to the structure, you may need much more force, and finally, if you are here on the nodal point here itself, it will be impossible for you to control. So, what it means is that based on my position of actuator, the controllability of the vibration mode will be actually determined, that whether it is controllable or not. Now, for a particular state x1 of a system, we will call it controllable when if all initial conditions x0 at any previous time t can be 0 or any previous time can be transferred to a future x1 in a finite time by some control function u t x0, and this also has to be a finite control effort. So, that means suppose we are in a 3-dimensional thing, let us say. So, I have a position here, and this is what, let us say, my x0 position with respect to 3 states, suppose, okay, x1 and x2 and x3. Now, from here I am going to some location here in this state space, which is some xt. Now, if I can go from this state to this state within a finite time t and with a finite control effort u, then only we will say that the system is controllable. And this is simply not possible in this case that I have discussed, that within a finite time, if you place your actuator here, you will not be able to control the vibration of this system. So, if all these states like that are controllable, then the system is completely controllable. If controllability is restricted to depend upon t0, then it is called controllable at time t0, that is within this time it is controllable, and if it is less it is not, if it is more it will be. If a particular output can be obtained from any arbitrary x0 at t0, then the system is called output controllable. So, these are some of the subdivisions of controllability of a system. So, that is the definition of controllability. How do I test the controllability of a system? Well, that is simple. If you have a controllability matrix called A, B, and then you can, if you have these A and B from this state space representation x dot equals to Ax plus Bu, you can develop your controllability matrix from this A B with the help of this particular formation of the matrix, which is B A B A square B to n minus 1 B, where A is of size n by n, and the system is fully controllable if and only if the rank of C equals to the number of the states. We will then say yes, this system is full state controllable from t equals to t0 to any time t, such that you will get a continuous input ut, and it will be able to drive it from xt0 to xtf within a finite time interval and with a finite energy. So, by checking this particular condition, if this is satisfied, we can say yes, it is controllable. For designing, before designing any controller in state space control, this controllability must be checked always. So, that is the first condition. If you get it checked, then the transformation, the inverse of the transformation will actually exist. Now, in some cases, controllability is considered to be a very strong constraint for a multi-degree of freedom system. So, there is a weaker definition of controllability, we call it as stabilizability. For example, if you look at this particular system x dot equals to Ax plus Bu, where A is like this 3 0 0 minus 2 and B is 1 0. The system has two roots, clearly it is only block diagonals, one at 3 and another at minus 2. This root is unstable. However, this root is stable. So, the controller, if the control effort exists only for the unstable mode at 3, and hence the system is partly controllable or stabilizable. So, this is the partial controllability or stabilizability as a special subset. Now, I told you that observer canonical form gives us, that is the dual problem of it, that is from the sense spin perspective, that a particular state x1 t at some given time is observable if the knowledge of ut and output yt over a finite segment of time can completely determine the states x1 t. So, this needs this pair. For controllability, we needed the A B pair, that is for controllability, if you remember, and for observability we need these, we need the pair of A C pair, we need the A C pair for the observability, and this is defined as OT equals to this particular thing, C C A up to C A n minus 1. The state matrix is considered of size n by n, and the system is fully controllable if and only if the rank of O equals to n, then only the system is fully observable. So, these are the controllability and observability are two dual forms. Now, let us say I give you a very simple example, that we have this x dot equals to x plus b u, where this is the A matrix 2 by 2, this is B and this is C. Okay, from by looking at it, we can say that it is it may be in a control canonical form, because these we have the coefficients here and only at the last row, and here the super diagonal is unity, rest terms are not there. So, anyway, we can first find out that what is the controllability, and then we can find out what is the observability. So, this is A, this is B and this is C. So, we can find it out. So, this controllability is what? It is B and then A B. So, for us what is B? B is 0 1, and what is A B? A times B, that means first row first column, that will give you that 1 into 0 plus 1 into 1. So, that is 1, and then second row this column. So, minus 2 into 0 plus minus 1 into 1, that will be 1 minus 1 into 1. So, that is my B A B. Okay. We do not have to consider the additional terms, because A is of 2 by 2 size. So, A n minus 1 B means actually A 2 minus 1 B, and that means A B. So, we have to go only up to B A B, and we get the controllability matrix. Let us call it as C with a special pattern in it, so that we do not confuse it with this C. So, this is C, and similarly I can find out observability again with a special pattern, and observability is C C A C n minus 1. So, we get the observability matrix for it. Now, if you check that for both C and O the rank is 2, which equals to the order of the system, hence this system is both fully controllable and observable. So, that is just an example to actually keep us tuned with controllability and observability. Thank you. In the next lecture, we will talk about how to apply all these concepts together for full state feedback control.